Today we'll be having a look at the following problem from the HSC Maths Extension 2 Sample Test Question 16C. So we have n is a positive integer and we need to prove the following inequalities of negative x to the power of 2n is less than or equal to 1 over 1 plus x squared minus this sum from k equals 0 to n minus 1, and have to prove it's also less than or equal to x to the power of 2n. Okay, so let's have a look at the first part. What we'll first have a look at is the this sum from k equals 0 to n minus 1. So we have negative 1 to the power of k, so we're going to have alternating plus and minus signs. And we also have this x to the power of 2k, so we have even powers of x. If we write the first few terms, you'll see we'll have 1 minus x squared plus x to the 4 minus x to the 6 plus and so on. And the final term will be negative 1 to the n and x to n minus 1, in fact, n minus 1 and x to the power of 2 times n minus 1. And what I'll do is I can write this as powers of negative x squared like this. So if I put the negative sign with the x squared together, we'll have 1 plus negative x squared plus negative x squared squared plus negative x squared cubed plus so on, and until it's plus negative x squared to the power of n minus 1. Okay, so now that we've written it like this, we can now use a geometric series formula. So if we make negative x squared equals r, we'll have 1 plus r squared plus dot 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 plus r to the n minus 1. And using the geometric series formula, we have r to the n minus 1 divided by r minus 1. And by substituting negative x squared into r, we have negative x squared to the n minus 1 over negative x squared minus 1. Okay, so now we have to add the term 1 over 1 plus x squared to this sum. So we'll have 1 over 1 plus x squared plus the sum of k equals 0 to n minus 1 of negative 1 to the k and x to the 2k. This will be equal to 1 over 1 plus x squared plus negative x squared to the n minus 1 over negative x squared minus 1. Okay, or in fact, I should say a minus sign, so that's a slight mistake. So we have a minus sign here. Okay, now we can cancel out these two instances of the minus sign, so we can instead rewrite it as plus negative x squared to the n minus 1 over x squared plus 1. Now, you see we have common denominators, so the 1 and the minus 1 will cancel out to get negative x squared to the n over x squared plus 1. Okay, so now we'll have a look at the absolute value of this expression. And the reason is when n is an even number, we have an even power of negative x squared, and this is going to be at least 0. But when n is an odd number, negative x squared is going to be at most 0, and number at most 0 to the power of an odd number is going to be at most 0. So what we'll do is we'll take the absolute value of this whole number. Okay, and absolute value is going to be positive or non-negative. So since x squared is a non-negative number, the absolute value will be the same as taking x squared to the n divided by x squared plus 1. And this is because x squared plus 1 is going to be positive. And we can see the numerator of the fraction will be positive because 2n is an even number. And now this absolute value is at most x to the 2n, and this is because x squared plus 1 is at least 1. So since you're dividing a non-negative number by a number at least 1, the absolute value is at most x to the 2n. And this means this number over here, since the absolute value is at most x to the 2n, it must be at most x to the 2n, but it must be at least the minus of x to the 2n. So since x to the 2n is a non-negative number, it must be at most the number, but it must be at least the negative of the number. And from here, it follows negative x to 2n is going to be at most this expression here. So we have 1 plus 1 over 1 plus x squared minus the sum of k equals 0 to the n minus 1 of negative 1 to the k and negative 1 to the k and x to the 2k. And we have at most x to the 2n. And this is what we were required to prove in the first part. So if you just have a look at the first part, that was what we were required to prove. So that completes the first part. Now, the second part is to use integration to deduce that negative 1 over 2n plus 1 is at most pi over 4 minus the sum of negative 1 to the power k over 2k plus 1 and less than equal to 1 over 2n plus 1. So using the inequalities, we have to use integration somehow. And the important thing here is, since this one expression is always at most this expression over here, it means when you take the integrals of both sides over some range, the integral of the left-hand side will always be at most the integral of the right-hand side, and similarly, this integral of the very right-hand side will be at least the integral of this. Okay, so let's take the integrals of each of the expressions, and we have to select what the bounds of the integral will be. So we have this over here, but we have to select the bounds in order to get what we want for this result. So what you can see is we have a negative 1 over 2n plus 1. So what we could try to do is, since we have a 1 over here in the numerator, we could try to guess the bounds could potentially be 0 to 1. So let's try 0 to 1 as a potential bounds. So that's a fairly simple guess for what the bounds could be. So this is something we could try first. And now, taking the antiderivatives of all the sides, we have x to 2n plus 1 negative over 2n plus 1 from 1 to 0 is at most. And now the integral of 1 over 1 plus x squared is tan inverse x from 1 to 0. And here we have to actually take the sum of multiple integrals, so we are actually minusing. We can actually integrate each term. We can take the antiderivative of each term here and find the sum of them. So what we can do is, each term we have x to the 2k plus 1 negative 1 to the k divided by 2k plus 1. And each of these are from 1 to 0. And this is summing from k equals 0 to n minus 1. And the right hand side will be x to the 2n plus 1 over 2n plus 1 from 1 to 0. Now the left hand side will be negative 1 to the power of 2n plus 1 is just 1, and we have negative 1 to the 2n plus 1 here is at most tan inverse 1 minus tan inverse 0 minus sum of k equals 0 to n minus 1. So this expression inside here, we're just doing it for we're substituting x equals 1 and minusing when x equals 0 is substituted. And when x equals 0 is substituted, we can see that x to the power of 2k plus 1 equals 0, so that will amount to nothing. So you just directly substitute 1 here, and we'll get negative 1 to the k, and 1 to the 2k plus 1 is just 1, and we have 2k plus 1 here. And this is at most, again, you can put 1 here and 0 here, and we'll get 1 over 2n plus 1, because 1 to the power of 2n plus 1 is 1. So now we have negative 1 over 2n plus 1 is at most. Tan inverse of 1 is pi over 4, and tan inverse 0 is 0. Now we have minus this sum as at most 1 over 2n plus 1. Okay, so let's have a look at this. Go back to what we needed to prove at the beginning. You can see we have the same inequalities as what we needed to prove, so this completes the second part of the question. And now it says hence deduce the value of this infinite sum. So this is k equals 0 to infinity. So we have this inequality involving a finite sum. We have to see how it works for an infinite sum. Okay, to see how it works for an infinite sum, we could take the limit as n goes to infinity of each of the sides. If you have a look at the left-hand side limit, we have negative 1 over 2n plus 1 as n goes to infinity, and since the denominator goes towards infinity, as n goes to infinity, this limit will approach 0. And similarly on the right-hand side, the limit of the very right-hand side, the denominator again goes to infinity, so the limit is also 0. And now, since we have these two limits go to 0, and since this expression pi over 4 minus the sum is squished within these two expressions, we can apply the squeeze theorem. The squeeze theorem, which says this limit which is squished between these two limits will also approach 0. Okay, so that means this expression here will approach pi over 4, because we have pi over 4 minus something approaches 0, so this sum should approach pi over 4 as n goes to infinity. And so we have limit of n goes to infinity of the sum of the negative 1 to the k over 2k plus 1 goes to pi over 4. And this is the same as saying the infinite sum k equals 0 to infinity of negative 1 to the k of 2k plus 1 is equal to pi over 4. And this completes the final part of the question. So we found that the infinite sum converges to pi over 4. So see how the sum looks like. We sub in some terms. We have 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9 and so on. This alternating sum and minus, plus and minus of 1 divided by odd numbers will converge to pi over 4. Okay, so that concludes this problem. So hope you enjoyed this video. Thanks for watching, and I'll see you next time.